Hi guys, welcome back to the vlogs.
It's Korea's birthday.
Why were you so quiet?
Happy birthday to Korea. Shout out to Korea at Korea Thacker. I don't know your username.
What's your YouTube?
Joe, birthday,
Okay, here we go.
That wasn't in.
6.7. 6.7 is indirect reasoning. Okay? Indirect reasoning. Here's the deal. We've been working on proofs where we list statements, we list reasons, right? Here's what's happening. Step 1, here's why. Step 2, here's why. Step 3, here's why. This is called indirect reasoning, okay? And indirect reasoning is a little bit different, okay? We use indirect reasoning because some ideas are difficult to prove with direct reasoning. So when it's hard to prove something directly, you're going to use indirect reasoning. How to write an indirect proof. Step 1, you state what you want to prove. So instead of starting with our givens, we're going to start with, this is where I want to end. Okay? Step 2, you assume that what you want to prove is not true. So you say, I want to prove that it is sunny outside during the daytime. Then you would say, it is not sunny outside when it's daytime. Okay? And then the third step is you're going to reason until you reach a contradiction. So what's happening is you're taking what you want to prove, you're changing it into the opposite of what that is. You're saying, okay, this isn't true. And you're proving that the not true statement isn't true, which then proves that your original statement is true. Indirectly, I'm proving it.
That makes sense.
Okay, so here's an example. Let's say it says, the restaurant is open all day on weekends. Okay? So then we would change it to say, assume it's not true. It is closed, not open. Okay? And then the last statement, you would say, reason until you reach a contradiction. Today is a weekday. This enables you to conclude it is a weekday and not a weekend, which means that's why it's closed and not open. Okay? So if you can do that, those are the 3 steps. Personally, I think indirect reasoning is much easier than setting up proofs. It is easier. Much easier because I'm proving something's not true that is. Makes it very simple. I'm like, okay, that's common sense. It's more of a common sense type thing. Okay. So indirect reasoning. Prove that if a whole number is squared, if a whole number squared is odd, then that number is odd. Okay? So we want to prove that if a whole number squared is odd, then that number is odd. So, what's our first step in this? The first step is, so 1, we want to prove that a whole number squared is odd. The number is odd. Okay. That's step 1. What's step 2?
Assume it is not true.
So how would I do that? What would I say?
A whole number squared isn't odd.
So it's what then?
Even.
Even. Okay.
Okay.
Whole number is even. Okay? Step 3, what? Okay, reason until I reach a contradiction. Okay? So, what would that be? What would be my contradiction? What do you know about even numbers? They're even, good. What happens if I square 2? What do you get?
4.
What happens if I square 4?
8.
16. What happens if I square 6?
36.
What? Okay, so when I square all those even numbers, what type of number do I get out?
Even number.
So what's my contradiction?
Every square.
Yes. So every time I square an even number, it's an even number. Boom, I'm done.
Woo.
So an even number times an even number cannot equal an odd number. Even number squared. Can't equal an odd number. There's your indirect proof. Well, we were trying to prove that a whole number squared is odd, then a number is odd, right? And we change it to say the whole number is even. So we want to come back and kind of restate what was up here. Does that make sense? So that is indirect reasoning. Is that easier?
Yes.
Yes, much, much easier. Okay, let's just talk a little bit about another one and see if you can help me figure this out. If I have this triangle, we're gonna say z, y, x. We're gonna make these little tick marks to tell us something. Then we're gonna have another triangle that looks like this. We're gonna name it ABC. And it's going to have little marks that look like this. Okay. It says in the triangles below, X and A are angles that are included, okay, or formed by pairs of congruent sides. So X and A are included in the pair of congruent sides. Okay? And YZ, segment YZ, is greater than segment BC. What rule is that we know that from? It says prove the converse of this theorem. What theorem is that? What theorem is it that says if the angle included in two sides that are congruent to the opposite triangle?
Is it the hinge?
It is the hinge theorem. Good, Carly, way to be resourceful. So, the hinge theorem. So we want to prove the converse of the hinge theorem, okay? So what's my first step?
Assuming
No, that's my second step. My
State
first-
what you want to prove. State what you want to prove.
Okay, so stating what we want to prove, okay? We want to prove the converse of the hinge theorem. Okay. So we want to prove converse of the hinge theorem. So, step 2 is what?
assume it is.
Assume it's not true. So, we would assume the opposite of the fact that the measure of angle X is greater than the measure of angle A, right? So we would say the measure of angle X is less than or equal to the measure of angle A. Okay? Because we know from the hinge theorem that if this side is greater than this side, that means that X is greater than A. Yes? Okay. So we're going to assume that the measure of angle X is less than or equal to the measure of angle A, because the opposite of being greater than can be less than, or it could be equals to. Okay? Now what do we have to do from there?
Reason until you reach a contradiction.
Reason until you reach a contradiction. Good. Okay? So, if they are equal, right? If X and A are equal, what do we know about these two triangles?
They are similar.
If the measure of angle X equals the measure of angle A, then I can do something with those triangles. What can I do with those triangles? I would have what?
Side angle side.
Side angle side. You would say that triangle X, Y, Z is equal to triangle ABC using side angle side. Well, that's not true, right? Because it tells us in the directions that they are, or they can't be equal. We know that they cannot be equal using side angle side, because then that would make the hinge theorem false. Okay? So this contradicts the equals. Okay? Now we have to contradict the less than. Okay? So if the measure of angle X is less than the measure of angle A, what does that mean? If the measure of angle X is less than the measure of angle A, what does that mean? If A is greater than X, what does that mean?
ZY is greater than CB.
Yeah, it would mean, if A is greater than X, it would mean that CB is greater than YZ. That's a contradiction, because the problem tells us that YZ is greater than BC. It's the end of your proof. So all you have to do is contradict both of those statements, the equal to and the less than, okay? And you're done. That's why I think this is easier than making a proof with statements and reasons. It's just kind of like, oh, well, I proved the opposite of both of those, so now I'm finished. Okay? That's what you're working on tonight. Okay, so tonight's homework is already, can you hurry up and stop that?
Yeah. Like, subscribe, comment, tweet me at David Dobrik. Anything else to add, Maya?